Hello and welcome to our UConn Quantum Computing Club that we have meetings on Tuesdays here at the University of Connecticut talking about quantum computing. And on April 7, we had the pleasure to have here Professor Victor Batista from Yale, from the chemistry department in Yale. And he gave an incredible talk about quantum machine learning on unconventional quantum computers. So instead of using conventional quantum computers, we mean using qubits. He introduced the concept of qmodes. So usually you have like a harmonic oscillator. Instead of having just 0 and 1, you use 0, 1, 2, 3, 4, all states, basically many states from the harmonic oscillator instead of just two. Instead of just two states as in the qubit platform. And so I want to share his talk, but unfortunately, because of my excitement in the beginning, I forgot to record. So we ended up losing like 5 minutes of it, which was just the introduction, introducing him and the first slide. But luckily, I can share the first slide. But in the first slide, he was just describing what is the conventional quantum computing, which is like basically defining the qubits. I hope you can see the first slide. That's the first slide. Defining the qubits in this superconducting circuits platform and how we actually see how we work with superconducting circuits. But then after that, when I started recording, he was just like talking about the unconventional part. So he defined everything properly. And then fortunately, I recorded this part. So then I leave you with his presentation, which is very nice, and I hope you enjoy it. Thank you.
If that is good, then we'll move to unconventional quantum processors, which are the ones that we've been studying for the last few years. This is a new technology that was also developed here at Yale by Rob Sholkoff, Steve Garben, and Michel Devoré. And their students and postdocs, Chen Wang was one of the former members of the Sholkoff's group, which look very different from the qubits that I was just describing, and the resonators that I was just describing. One thing I wanted you to remember is this coupling between each qubit and a resonator. By a resonator, you can think is a quantum harmonic oscillator. By a qubit is a two-level system, and they're coupled, and therefore the harmonic oscillator can excite or de-excite the two-level system. And that's the way these conventional circuits work. Here, the resonator looks quite different. The resonator is this box of, this block of aluminum or this block of copper that has a hole. And here it has two holes, but this one has a single hole. And where you can put photons inside of these cavities. And by putting photons, what I mean is you can send an electric pulse that polarizes the walls of these hole, or the walls of these two holes here inside of this block. This whole block is in the same kind as I showed before, and this whole thing is frozen at 10 millikelvins. But through these wires from here, you can polarize the walls. In the same way as when you send a pulse that touches each of these dots, you can polarize these resonators, you see. But this is a 2D resonator because it's a coplanar arrangement, while this one is a 3D resonator because it's a whole cavity inside of a block of metal. There's another half that goes on top and is screwed through these screws here, and then so you can think of this as vacuum inside of this cavity where you put photons. In this case, are microwave frequency photons, and due to the dimensions of this wall and the frequency that is applied. The reason why they use microwave frequencies is because you can control these pulses very well in the microwave frequency range. And something else that you can put inside of these cavities are these quantum circuits. Like, this is made with lithography. Also, this is a wire of aluminum. These are 5 microns. It's a tiny circuit where you have, in this case, three Josephson junctions here and another one there. So each Josephson junction corresponds to one of those qubits I was describing before, the sandwiches of aluminum with aluminum oxide in between. This whole construct is each of these two parts of the circuit is what is called a snail. And it has not only an energy surface that looks like a like a two-level system, but it looks more like the potential of a pendulum. This is an anharmonic potential where you can make use of not just the ground state and the first excited state, but also the higher energy levels. And you can modulate that nonlinearity by also applying extra pulses that give extra components to the Hamiltonian of this quantum circuit. But something I want you to bear in mind is, okay, if this is the resonator, right? How does the resonator interact with a qubit? So one way is to inject a qubit in this slip of sapphire. You see that it comes into this slot and gets inserted. And it has here engraved in this piece of sapphire a qubit with three plates that are capacitively coupled to the qubit. One plate is capacitively coupled to a coplanar resonator here, so that one can control the qubit by pulsing this resonator. And then the other two are coupled to these two cavities. So now the qubit can interact with the modes of the resonance modes of these two cavities in the same way as this qubit interacts with that resonator. See? So the only difference is that here the polarization is not the polarization of the strip of wire that is folded here, but is the polarization of each of these cavities, or the polarization of that cavity. Here you can also put this other type of transmon or qubit, but instead of being a qubit, it's a qubit because you can access d energy levels rather than just two. Now, one way of using these unconventional quantum processors is in the same way as we use here the qubits to represent the quantum state and the resonators to manipulate the state of polarization of the register. By using multiple qubits inside of this cavity, for instance. But another way is to use the qubits to manipulate the state of polarization of the cavity, and therefore use the state of light inside of the cavity as the register, as the quantum state that one manipulates and measures. And that's the way that is very promising, because in that case, you can represent a quantum state inside of this cavity using the ladder of Fock states that correspond to all the excited states of polarization of this cavity. That is, in principle, an infinite number of energy levels. Of course, in practice, you cannot use them all. You can only use, the set of energy levels that currently you can use up to 16 energy levels of that cavity, but that corresponds to 4 qubits, right? So in that way, you can have hardware efficiency by using the state of polarization of the cavity as the register instead of using the qubits, the array of qubits as a register. So what I would like you to learn in this presentation is now how to use these unconventional quantum processors for machine learning. And the reason and we are interested in machine learning with these devices is because a wide range of applications in chemistry could make use of these very compact quantum computers, and that offers a quality of coherences that are unachievable with conventional quantum computers. Here, what you see here at the bottom is that these cavities have ultra high quality factors, and that means of 10 to the 8th to 10 to the 10th, which means how many cycles of oscillation of the state of polarization of this cavity, it has to go before the energy that is initially stored in the device decays by a small percentage of that amount. With conventional quantum processors like these coplanar arrangements, this quality factor goes only up to 10 to the 6. So these are at the moment the state of the art in storage, in quantum storage of quantum information. And that's why it enables to preserve the state of polarization for much longer than with conventional quantum computers. So the question you have now in mind is how do I actually train this computer, and how we use it to make predictions of unknown questions, right? So one thing I want to show is, for instance, one of the processors that we have simulated for making predictions of molecules, like the ones that you have here in this table. What we've done was to find out how to use this device to predict the solubility of molecules. So if the solubility is in a mixture in water, for instance. So you have different molecules. The question is how you encode these molecules in the state of polarization of these cavities, and then how you make measurements in these cavities so that it would predict the property that you're interested in. As a final result, what I'm showing here in this plot is the correlation between the predicted value of solubility of thousands of molecules of this size, more or less, as compared to the experimental values. And you see a strong correlation showing that these devices can be used for predicting properties of molecules. And in this case, it is illustrated with solubility, but we can also predict toxicity of molecules or any other properties for which we have data that we can use for training these systems. So next, let me explain how we train this device to make these predictions. What we have is what I'm representing here are the matrices, you see, that you have to apply in order to advance that vector that corresponds to the state of polarization of the cavity. And by CD, I mean conditional displacement with parameter beta. That means that the harmonic oscillator that represents the state of light in one of these cavities is displaced by a pulse that displays that coherent state in terms of the real and imaginary components of the quadratures of that quantum harmonic oscillator, as defined by this parameter beta. And so that conditional displacement means that I can displace the state of light inside of the cavity conditional by the state of the qubit, if it is in the ground on the excited state. Only if it is in the qubit in the excited state, I will displace the qmode. This other set of matrices is equivalent to having applied a knot to the qubit and then a conditional displacement to the cavity. And here, this green block represents all that. Now, these are two of the transformations that we can perform. One is a rotation of the qubit, and another one is that ECOT conditional displacement, which corresponds to a knot on the qubit and a displacement of the cavity. In a way, these are the constituent pulses that can come down the wires to polarize the cavity and the qubit. And if you repeat many of this sequence of rotations and ECOT conditional displacement a sufficient number of times, you can prepare here an arbitrary quantum state of the qubit and the qmode. So this is universal capabilities, or universal quantum computing is enabled by a sequence of these pulses. So you don't need Hadamard gates, you don't need any of the elementary gates that you use in conventional quantum computers. Just with rotations and equal conditional displacement, you can achieve a preparation of an arbitrary quantum state in this way. So with that in hand, what we are going to do now is we are going to encode molecules. In this case, for instance, if you want to encode ethylene, which is a molecule that we might be interested in, what we do is we represent the carbon, the double bond, and the other carbon in terms of a list of numbers or a tensor associated with the carbon, a different number corresponding to the double bond, and then another number for that is usually what you do in conventional machine learning. Here in this quantum computer, what we're going to do is we're going to assign a parameter for the rotation of the qubit, and that corresponds to carbon whenever the molecule has a carbon in its representation. And here we are writing this representation of molecules by using the dictionary of what is called SMILE strings. And then the conditional, equal conditional displacement también also has a displacement parameter that corresponds to carbon. The double bond will have its own corresponding parameters, and then this next carbon has the same parameters as this one. So after applying this rotation and equal conditional displacements in this sequence, what we have here is a quantum state associated with light inside of the cavity and a state of polarization of the qubit that corresponds to this molecule because we encoded the molecule according to the parameters of these pulses that we have applied. And then what we can do is to define another block of parameters that correspond to learnable parameters, parameters that can be learned. One second.
Does anyone have any question?
So in the same way as we have just encoded a molecule, we have a set of parameters that are the parameters that are being learned to make predictions of the properties of the molecules that we have encoded here. So the way we make a prediction of properties is by making a measurement of the quantum state after passing it through this block of learnable parameters. Here we have initially random parameters for these learnable parameters. Here we have the parameters of the molecule that we just encoded. And now we're going to make a measurement here. For instance, a measurement of the electric field of corresponding to the electric field inside of the cavity. And that is the quadrature or expectation value of position that we're going to assign to the property of the molecule that we encoded. And then we train these parameters so that the expectation value that we get here corresponds to the property of that molecule. And we do the same thing for many, many molecules. And at the end of the day, we minimize the error between the predicted value of this expectation value as compared to the property of that, for instance, the solubility or the toxicity of the molecule for each of the molecules of the batch. So with that in hand, now we can encode an arbitrary molecule for which we know nothing about its solubility or its toxicity, run it through here, make a measurement of quadrature, and predict its solubility. And therefore, that's how we proceed with the supervised quantum machine learning using this unconventional device after training the pulses that are applied to the device to reproduce the properties of a batch of molecules for which we have experimental data. So with that in hand, I want to stop here and ask whether you have any questions on how to use these unconventional quantum processors for supervised quantum machine learning.
I have two questions about the qmode and the qubit. It is exactly the mode from the cavity, right? It's just a harmonic oscillator. It's not like, because what I'm thinking about, thinking the care parametric oscillator, so something advanced that you have to drive and then you have the squeezing. It's not that, right? So it is the Q mode, the harmonic oscillator, and the
Yes,
qubit from the transmon, that anything that you're
exactly,
putting inside. And how they
exactly,
are coupled to each other is based on this drive or anything that you can do.
exactly.
Is it that?
That's it. Yeah. So here, if we don't put, these type of devices inside, and we don't use these ones to represent the quantum state, but rather we use the cavity. Then the cavity is a harmonic oscillator. So here you have a Hilbert space of the quantum harmonic oscillator, and then the Hilbert space associated with the two-level system. So overall, you have a Hilbert space that is the tensor product of the Hilbert space of the qubit and the Q mode. And if you have 16 modes, 16 levels in the Q mode that you can make use, and you have two energy levels for the qubit, then that's your basis where you represent your quantum state. Yeah,
I can ask my question later. So there is another question from the meeting.
sure.
You can open the mic and
Can you hear me?
Yes,
My question is a bit long. May I ask it anyway?
absolutely.
Regarding the smiles encoding for property prediction, I am developing a hybrid algorithm
Uh-huh.
using the QAOA base for quantum molecular discovery. And I want to know how can I use the bosonic system to help predict how the selected molecules will behave?
Mhm. So you're running QAOA as an optimization.
It's an hybrid algorithm I'm developing. It's kind of
Mhm.
mix of a classical and the QAOA, but I'm
Okay.
achieving better results than the brute QAOA and for example, the greedy algorithm.
Mhm. Yeah. So, and are you describing the dynamics of molecules, or what system are you evolving?
For yet, I'm just trying to discover the biggest diversity between n number of molecules, for example, 30 or 16, but I'm trying to do in a way that I can use the selected molecules to predict what they can do.
Mhm. Yeah. So one approach that you can follow is this one, right? So for each of these molecules that you encode with these parameters, you make a prediction of that behavior that you assign to be Y. For instance, the molecule um, might react or not react, for instance. So you can have a label associated with that behavior, let's say 1 or 0, and try to train these parameters so that when you make a measurement of this quantum state for the molecule that reacts, you get a 1 here, or you get otherwise a number larger than 0, let's say. And for the ones that don't react, you get a number smaller than 0 for this Y. So in that case, you can classify molecules according to their behavior. So you can adapt the scheme for the type of application that you have in mind, and it would does not require any changes. It's just retraining with the labels corresponding to the behavior you might be interested in. Does that make sense?
Does. Just another fast thing. Is there any way that I can access those different quantum computers? Because now the one I'm currently using is the IBM FES
Right.
127 qubits, but I don't think it
Yeah.
can run such types of
Yeah.
neural networks.
Right. These ones are mostly experimental, so you have to collaborate with the groups that are actually developing them. That's what we've done. and we are currently collaborating with other groups that have similar devices. But also there is a company, Quantum Circuits, that I mentioned at the beginning, that has recently partnered with D-Wave, so this one, and they make their platform accessible to some groups, so you can contact Quantum Circuits plus D-Wave, and they have at least this type of processors currently are being used to represent qubits with pairs of cavities. So if you have a photon on the left is 1, or if you have it on the right is 0. So each of these pair of cavities corresponds to a qubit, and they call that the dual rail approach. So an array of these type of devices corresponds to an array of qubits. And if you want to try that technology, you can contact them, and they're welcoming collaborations with research groups interested in using their device.
Thank you.
You're welcome. Other questions?
I just have one very, I don't know, just how do you calculate the solubility of the molecule at the end? I get it, the whole optimization, but I didn't get it like the X and how it turns to Y.
Yeah, so for each molecule, you know what is the solubility, right? So you're going to make a measurement on this final quantum state, which in this case is the measurement of expectation value of position that corresponds to the measurement of the electric field, or the quadrature, and you assign that value to the property, to the solubility. And if you don't match the solubility, then you adjust these parameters until it matches. Then you do it for another molecule.
Okay. Thank you.
And then after training with many molecules, the parameters they end up having in these blocks work for all of the molecules. And you can run in an unknown in the same way by encoding it here, and it will predict its corresponding property.
Okay.
Is this making sense, or?
No, I get it. I just missed this part probably, and then now I understood. Thank you.
Okay, so something else that we've done recently is to generalize this approach that is called supervised machine learning to generative machine learning. So one of the goals of chemistry is to make new molecules. In engineering, you might have the challenge of developing new materials or new devices, right? So in that way, traditionally, when you face a challenge, you engineer a procedure that will generate that new device or that new molecule according to principles and concepts that represent the state of knowledge in that field. Now, with machine learning, things are changing, and that it is found that using data rather than knowledge enables also us to design new molecules and new devices, and do that more efficiently than with an algorithmic approach, a traditional algorithmic approach. So that's what we have done here in this recent paper. It's called Cobra, and I forgot to put here the reference, but it's already published. So it's a quantum autoencoder for de novo protein design, but it can be used for de novo design of devices or de novo design of materials. Bottom line, what we are doing here is developing a quantum version of the autoencoder. So for those of you who have not heard of what an autoencoder is, let me explain it in simple terms. What you have here in this block, you see all these matrices that are applied here, is an autoencoder where you input a state, which is just a list of numbers. You transform that distribution of amplitudes into a new distribution of amplitude that might look like this Gaussian. And then that process by transforming the input into a Gaussian is called an encoding. And then you have something analogous to this other half, which is called the decoding, where this Gaussian is transformed back into the initial input that you provided. So that is autoencoder because it regenerates the same state as you input, right? The only difference is that you transform halfway through that initial state into a Gaussian. And so this is what is called an autoencoder. So what you have in these blocks are just pulses that correspond to the same type of blocks of pulses that you have just described for supervised machine learning that are being trained so that for each of these samples, you end up having a position inside of this Gaussian distribution, right? So basically, if you have thousands of input states like this one, then you transform all of them into a distribution that looks like a Gaussian here in what is called a latent space. How you ensure that this latent space looks like that, so that the distribution of samples that initially might have an arbitrary distribution is transformed into a Gaussian distribution, is by comparing the state that you generate here with a Gaussian, and then by measuring the fidelity between that state that you have here and the desired distribution that you want, you can adjust the parameters of the encoder to make it as similar as possible to that desired distribution. And then same thing is for the decoding. You train all these parameters, so at the end you generate a state that looks like the original one. So the fidelity between the initial and the final and the initial is as close as possible to 1. So with those two losses, now we have a way of parameterizing the pulses that are applied to this circuit. And then once we ensure that the loss is very small, because the sum of these two losses is very small, then what we can do is remove the encoder and sample from this Gaussian distribution and generate samples by decoding that would correspond to the type of samples that you use for training. So you see, because since you encoded all of the samples, in this case were proteins that were encoded into these amplitudes of the input state, then when you decode from this Gaussian distribution, you would generate a set of amplitudes that can be representing the type of samples you use for training. So that is what is called de novo design, because once you have a batch of data associated with, let's say, proteins in this case, but it could be materials, then you can train your device. In this case, you train the pulses of this device so that you encode all of those samples into a Gaussian distribution. And later, by sampling from that Gaussian distribution, you generate samples of the type that you use for training. In this case, are proteins, but you can do the same thing with pictures of humans. And then you would be generating here pictures of humans from sampling from this distribution. In chemistry, this is very important because many times we have molecules that are of a given type, and we want to generate other new molecules of that type. And instead of trying to think about how to do that, we just train this device and then we sample from this distribution and it would generate. Here we demonstrated how to do that to generate metalloproteins. These are proteins that bind metals. You see, like this ball here. And so what type of primary sequence for that protein would be good to click a metal? And when you change the metal, you probably will have a different sequence of amino acid residues. And that is the question that this device resolves. And what you see here is a protein is represented by letters, a list of letters. Each letter corresponds to an amino acid. Those letters can be translated into numbers according to a dictionary, and those are the amplitudes of the input state that is provided here. And the same thing at the end, once you have these amplitudes, this list of of numbers, you can translate that into letters, and those letters correspond to the amino acid residues that correspond to that protein. And passing that list of numbers to AlphaFold, you can get the structure of the protein and see whether, in fact, the metal is being clicked by the right type of amino acid residues that usually bind to that metal. And that is what this device does. The question you might have in mind now is, how do we measure fidelity, right? Because we need to train the device by minimizing the loss, by comparing the generated state, for instance, here in latent space, to a Gaussian distribution. And that can be done with what is called a swap test. And for those of you who are doing quantum computing, you might be familiar with this swap test, which is that when these two states are the same, you see, and you entangle them with this ancilla qubit, you can make a measurement of the ancilla qubit and get a 1 here, so an average value of 1 with probability 100%, when these two states are identical. So when the overlap between these two states is equal to 1. So without observing the quantum state, you can observe this ancilla and detect whether the state you prepared is identical to this other state or not. And the way you implement this swap test is simply by rotating each of the qmodes with these two gates, and then using a beam splitter. That is a method that has been known for a long time. So in that way, we don't need to do quantum tomography. We don't need to observe whether here we have a Gaussian distribution or not. All what we have to do is a swap test between whatever state we generate here and an input state that we initialize to be a Gaussian. And by measuring an ancilla, we will have an estimate of this loss. And the same thing when we compare the initial with the final state, we do exactly the same thing. We do a swap test between the initial and the final state after storing the initial one as a copy and comparing the final state that is generated by the circuit with the copy of the initial state with this swap test. So at this point, I want to stop and see whether the concept of an autoencoder was understood, how to train this autoencoder with a data set, and then how to use the decoding process to generate new samples of the type that we use for training this device. And finally, how we estimate the loss to ensure that here in latent space we have a Gaussian distribution, and here we generate an output state that corresponds to the input. That means we have good reconstruction of the input state. Is all that understood, or we have any questions?
Yeah, we have one question here.
Okay.
Just wait, just one.
Yeah, hi. I don't know if I fully understand the role of the Gaussian and why a Gaussian specifically.
Mm-hmm. Yeah, so a Gaussian distribution is usually very simple to generate with a qmode. You see, because the state of a harmonic oscillator, of quantum harmonic oscillator, looks like is a Gaussian. So if the circuit is, or the state is stored in a cavity, then that Gaussian distribution would be easy to generate. And even a displaced harmonic oscillator would look like a Gaussian that is displaced. So if we encode the inputs into this Gaussian distribution, it's something we can easily use later to generate samples without having to worry too much on how we initialize the quantum circuit. But of course, you're right. We could use any other distribution that we might be interested in, if we have an easy way of generating it for generating new samples.
Thank you.
Yep.
I have one question as well about the fidelity.
Mm-hmm.
Because you're saying that you can measure basically 0 and 1, so you cannot can you know, like, for example, comparing that they state with the Gaussian, if it's like 90%, like from the fidelity, or is based
Yes.
on shots, on number of shots, or is just like always 0 and 1?
Right.
Like,
So
is on yes or no, or multiple
no,
shots to get like a distribution?
okay. So imagine here in this cross, you generate an arbitrary state, right? And you want to know whether this one is a Gaussian. So
Yeah.
what you do, you prepare in this other Q mode a Gaussian,
Mm-hmm.
and then you entangle these two Q modes with a qubit. In this way, you apply Hadamard to the qubit, and then you do a conditional swap. That means you take this quantum state, you put it in this cavity, and you take this quantum state and you put it in that cavity. This
Yeah.
is what this transformation is doing, conditional for the qubit to be 1. Then you
Mm-hmm.
apply a Hadamard gate to the qubit, and you measure. What you're measuring here is a number. Now, when you repeat this experiment many, many times,
Okay.
you will get an average of 1 or -1. Each time the qubit is in state 0, you get a 1. When the qubit is in 1, you get a -1. The average of all those ones and -1s will give you here an average number that when these two are equal to each other, this number is equal to 1. The average is equal to 1. That means you always get 0 here.
Mm-hmm. Mm-hmm. So
And
my question was more like if you were doing like many shots as like many runs, so
yeah, you
that's
have to
so
run
then
this.
you have like 90% of or 80%, it's something like.
Yeah, you have to run it thousands of times. In fact, when you estimate this average, and if you want to get, the average value with an error of epsilon, you see, for instance, you want um, that the number is as close to 1 with a plusless, with an error of epsilon, then you have to run this circuit 1 over epsilon squared times. You see,
Mm-hmm.
so that's the error that you would have in this average. So even if these two are identical, then this is a stochastic measurement that will give you an average value close to 1, but with an error of epsilon, and that error is determined by 1 over epsilon squared number of times that you run the circuit. So it's always by shots, right? The way these circuits operate. Okay, so I think I covered most of what I wanted to present, but I don't know how we are doing in time and how you want me to proceed.
7:02, you can proceed since we started a little bit later. You can proceed like for like more 5 or 10 minutes if is that okay for everybody?
Sounds good. So this is one of the results we generated with this de novo quantum autoencoder. You see, after generating the amplitudes, we decoded into amino acid residues. We gave that list of amino acid residues to AlphaFold, and this is the structure that AlphaFold generated. What you see here, we were trying to generate proteins that bind zinc, right? And what you have here, these gray balls are zinc ions, zinc 2 plus ions. And what you see here next to them are the side chains of amino acid residues that usually click to zinc, in this case, cysteines and histidines. So what this is showing is that the structures that are generated by these quantum autoencoder make a lot of sense, because not only they have the type of amino acids that we need to bind that metal, but also when the protein is folded, it adopts this configuration where those residues are next to each other in space, although not in sequence, and enable to bind metals just in the way you would expect. So that is very promising, and we are currently extending that technology to generating new materials in collaboration with NVIDIA and a company called Mitre. Another development that we have recently developed is what is called this hybrid transformer architecture. See, we collaborated with NVIDIA, a group at NVIDIA, and these are the scientists from NVIDIA that collaborated with us to see whether we can use one of these quantum processors for running ChatGPT more efficiently, right? So, so what we have is that in the process of what I'm representing here is just one layer of the what is called the self-attention mechanism of ChatGPT, where you have an input that is transformed into an output. So this is a list of numbers corresponding to your input. In this case, the input is a molecule, which given by these characters associated with small strings of that molecule, but you can type something here and you have an input that is translated into a set of numbers. And then that list of numbers is transformed into a new list of numbers that corresponds to the output. That is the autoregressive model of ChatGPT, that if you repeat this set of transformations, each of these blocks correspond to a matrix that evolves that vector from the initial to the final state, then you repeat this process many times, then you get an output that corresponds to the output associated with the input. So for instance, you can use this for translating a sentence from one language into another one, or in this case, we can translate a molecule into a list of properties associated with that molecule. Now, that can be all done with classical transformers. But what we wanted to do is to see whether a quantum processor could assist this process and maybe enable more efficient functionality of that transformer architecture. So one step in the process of transformation of this vector into the final vector is what is called the quantum attention mechanism, the self-attention mechanism, that here we transform into quantum attention. The self-attention mechanism is something very simple. What you do is you have an initial input that corresponds to a vector, a list of numbers, and you multiply that vector by 3 different matrices that have entries that are going to be adjusted according to the functionality that those matrices will perform. So those are the learnable parameters correspond to the entries of those matrices. So starting with random numbers for the 3 matrices, you transform that input vector into 3 vectors, which are called query, key, and value. So you just triplicated the initial vector into 3. They are not identical because the 3 matrices that you use to generate the query, key, and value are different, right? Then what you do is you do an outer product between query and key. That means that you generate a matrix that corresponds to the query key transpose, right? So with that matrix, now you do what is called a softmax transformation. That means you divide the exponential of the entries of each of the entries of that matrix by the sum of the exponentials, very much like a partition function. And that is called a softmax transformation. So bottom line is you started with a vector, you generated 3 vectors. With 2 of those vectors, you generate that matrix. Now that is scaled according to the softmax transformation. And then you use that matrix to multiply the 3rd vector, which is called the value. So when the value is multiplied by that matrix, you generate a new vector, which is what is the output of that self-attention mechanism. That's what ChatGPT does. So once you get that final vector, you have these other layers that are sort of trivial because you add normalize it, you pass it here through a feed-forward network, you add it to that transformation, you pass it to a linear layer, you softmax, and that this final softmax gives you an output that in a way is a set of outputs corresponding to the probabilities associated with that softmax transformation. Now, a key aspect is the building that matrix, right? So for building that matrix, what you do is for each token of the input, you have a tensor or a list of numbers that you need to dot product with each of the elements of the other tokens in the input. So you have to compute n by n dot products that build that outer product of the query and the key. That dot product can be efficiently computed with a quantum circuit according to this circuit that is called a Hadamard test. So basically what you have here is a qubit. Here you have a qmode, or a set of qubits that represent the query and the key, that you encode into this with this unitary transformation, and then you measure this qubit. And if you repeat these measurements many times, what you get here is the dot product between the query and the key, which is what you need for each of the entries of the softmax matrix. So this is what we've done with NVIDIA, showing that when each of these tokens corresponding to the input is embedded in a very long representation, then you could compute all those dot products more efficiently with this quantum circuit. And that is another way of using quantum processors to assist machine learning applications. And here's another way of using quantum processors for generating molecules with a given property. Many times what we have is the challenge of designing a molecule, for instance, that binds to a specific site of a biological receptor. You know, when you're designing a drug, that's what you want to do, design a molecule that clicks in a specific pocket of a biological receptor. And of course, if you have a very long list of molecules, you can try one by one and see which one clicks, right, and which one binds in the pocket. In that way, discover a molecule that might block that active site and therefore prevent that enzyme to work. Usually we want to target enzymes of bacteria, so that, and these are enzymes that we don't have, and therefore we can kill the bacteria without killing the humans. Now, that process is very tedious, and classical computing usually leaves that. It takes a very long time to find new molecules that target specific receptors. So what I'm showing here is a quantum approach for de novo design also, and based on a circuit that starts in vacuum, is transformed with a set of pulses, and generates here at the end a state vector that is used as a sampling distribution. So if at this point I make a measurement of the qmode, basically I determine how many photons I have in the cavity, I can transform that number of photons into a binary representation and have a bit string that corresponds to the sample that I extracted from that state vector, you see. And then with a bit string, I can decode it into a given type of molecule. So if I have 101111, that corresponds to ammonia. If it is 10111100, that corresponds to water, and so on and so forth, right? So what I can do now is to do exactly that. Start with random numbers for these gates, sample from that state vector, translate that into a molecule, check the property that we want, whether it binds or it doesn't bind, and then update the parameters of the quantum circuit so that next time I sample from that distribution, I get a molecule that binds better, right? And that's what we've done here in this paper. We have a given biological receptor that we wanted to target, because this is what we need to block in order to prevent the growth of tumors in cancer. And we iterated until we found a molecule that has the right type of interactions with the surrounding residues in the pocket of that protein that we want to target. So we have demonstrated that this quantum ensemble variational optimization algorithm enables the quantum circuit to generate bit strings that encode for the type of molecule that would be useful for treatment of therapeutic treatment of oncological applications. Another problem that we have recently addressed is the design of vaccines, messenger RNA vaccines. You see, what you have here is a list of letters, right? Which correspond, in this case, I see is the list of letters corresponding to the DNA that is generated after translation of the RNA that is injected into our arm. So Moderna has designed this list of RNA bases that encode for this specific protein. So when we are injected this vaccine, our body generates this protein, which happens to be the protein that coronavirus has in its shell, in the surface of the cell, on the surface of the virus. So when we start generating this protein, our organism thinks that it has been invaded by a virus, right? So it develops antibodies, which are proteins that bind to this protein and block it. That is an immunological response to the vaccine. When the virus comes, we have those antibodies, and therefore they can attack and inhibit the virus. Now, that is how messenger RNA technology works, how the vaccines for coronavirus have developed. This technology is currently being used for a wide range of applications beyond treatment of viruses. But the issue is that this sequence of RNA bases correspond to a very long string that ends up being folded by hydrogen bonding of the RNA bases. And it really needs to be folded in order for our cells to translate this encoding into a protein. It's easy to generate a protein to be able to read this structure of the vaccine has to be sufficiently packed. And what happens at room temperature is that those hydrogen bonds break and this structure opens and it doesn't express well. So we don't generate enough proteins. And since we don't generate enough proteins, we don't get antibodies and the vaccine doesn't work. That's why the vaccine needs to be transported at very low temperatures to prevent those hydrogen bonds from breaking. So the question that many of these developments have is, how do I design a sequence that has enough hydrogen bonds, where it is sufficiently well packed? And the thing is for each amino acid residue, we have different codons that can be used to encode for the same amino acid residue. So we have many possible sequences that would encode to exactly the same protein. And if you count how many vaccines would encode to exactly this spike protein of coronavirus, the number is astronomical. In fact, it's much larger than astronomical and cannot pass. Is 10 to the 632 possibilities. So for this protein, you have 10 to the 632 possible vaccines that you can have that would encode to exactly this protein. Obviously, Moderna has not checked them all because it would be impossible, right? So what we are trying to find out is whether with this quantum ensemble variation optimization algorithm, we can find sequences that have not been found because of the astronomical number of possibilities. And we're using for this approach exactly this approach that I was describing here, where we generate a state vector with this circuit from where we sample a bit string that encodes to a specific sequence of codons associated with that protein. And since this one has 1,200 amino acid residues, and each amino acid residue requires 3 RNA bases, this is a very long list. So what we need is many qubits. But instead of using qubits or many qmodes, what we have developed here is what is called a holographic implementation, where we can repurpose some of the qubits or qmodes by measuring them at an intermediate point of the circuit and resetting them according to the representation of other elements of the circuit. So that is the holographic approach as applied to the novel design of these messenger RNA sequences. And these are the codons, for instance, two different columns and that represent the same amino acid residue. This is alanine that can be represented by these two other columns. So what we've done is to identify the optimal set of codons to maximize the number of hydrogen bonds. And what you see here is, this is for a small piece of RNA that we are able to generate the representation of codons so that the number of hydrogen bonds or cliques that you have here represented is maximized and is maximally folded. And here's an application for a longer messenger RNA sequence. And you see here, each of these pairs are hydrogen bonds, indicating that the method works in terms of generating sequences of with very good stability and very good thermal stability. So I hope that with that, I illustrated how these devices can be used for a wide range of applications, from molecular design to de novo protein design with variation autoencoders, and to the design of messenger RNA vaccines with a good thermal stability. Are there any questions regarding this last part?
Any final question? No? I just have one more broad question, Professor.
Yeah.
If any student from physics, chemistry, or engineering is interested in this new approach with qmodes, because when you think about qubits, there are many platforms that you can go with to learn it by yourself. But if you want to do like similar things with qmodes, where do you learn it? What would be the best way to start it?
There is a recent review by Steve Garvin and others on the sequences that they can be used for this type of applications. And we also have a perspective article that in our webpage where where you can read about this. So let's say with this article, Simulating Chemistry on Bosonic Quantum Devices, gives you an introduction to this technology. You see here is the Q mode and the qubit, and then the sequences that can be applied. So this is one introductory article that I would recommend. There are very good co-authors here. And so one thing is that although here we made an emphasis on chemistry because this is a chemistry journal, there's nothing particular about chemistry here that cannot be generalized to engineering or materials. So I would suggest starting with this, and then I can also send you other reviews and also Jupyter notebooks. We have, most of what we published, we publish with codes that can be used for this type of application. For instance, here we have simulating electronic structure on Bosonic quantum computers. So if you want to do electronic structure calculations of materials, you can do it with these cavity with qubits, qmode with qubits, and then at the end you have the GitHub with all the codes on how to apply all of these transformations with the qmode representation. So see where the GitHub is. And here at the end, so here we have all the codes for generating these ansatz and the Jupyter notebooks for universal qubit qmode ansatz optimization are provided here. So, and you can also reach us reach out to us and we can help out.
Okay, that's perfect. I think then we wrap it up. So thank you very much, Professor. Thank you for everybody, like virtually and the people in person. So thank you, and that's it. Thank you.
Well, thanks a lot. Take care.
Take care.
Thanks, Edson. Bye bye.
Thank you, Leah.
You know?
See, thank you.